Hello, this is Ms. DB. Today we're going to talk about exponential decay. So we're going to write and evaluate exponential expressions to model decay situations, and we'll also graph them. So our general function of an exponential function is a times b to the x, where a is the initial value and b is the growth factor. And for exponential decay, b must be between 0 and 1. You'll usually have that given to you as a decimal number, like 0.75 or 0.12. And here's again the exponential function, and we can see that it's decay if b is between 0 and 1. That's the growth factor. So you're going to answer this true or false question, and then you're going to get into some graphing problems. So here's an example of how to graph exponential decay functions. We're going to replace x with whatever the x value is from your table, and then you'll solve those and figure out, here's an example of graphing, what the graph looks like. You can graph these using these points that you found, but you can see that they get a little bit tricky to graph because they get small so fast. Or you can type it into Desmos and take a screenshot, or GeoGebra or Sketchpad. So let's look at a problem like number 3. There's an extra column here. I'll delete that. Alright, so it says we have our function 3 times 0.5 to the x. So we're going to have to multiply 3 by whatever we get when we plug in -2 is our first x value. So 0.5 to the -2, that's the same as 1 over 0.5 squared. So 0.5 squared, get your calculator out. 0.5 to the second power is 0.25. So we really have 3 over 0.25. So 3 divided by 0.25 is equal to 12. And you can do this with fractions instead of decimal numbers if you prefer, and you'll get these values a little bit differently, but you'll get the same answers. Let's do 3 times 0.5 to the -1. Well, that's the same as 3 times 1 over 0.5, because 0.5 to the 1 power is just 0.5. So we have to do 1 divided by 0.5. That's 2. So we have 3 times 2, which is 6. And then we have 3 times 0.5 to the 0 power. Well, anything to the 0.0 or anything to the 0 power is 1. So we really have 3 times 1, so we get 3 here. And then we have 3 times 0.5 to the 1 power. Well, that's just 3 times 0.5. You can do it on your calculator if you want, but half of 3 is 1.5. And then we have 3 times 0.5 to the second power. 0.5 to the second power is going to be 1/4, or 0.25. And now we have to multiply that by 3, and we get 0.75. And then finally we have 3 times 0.5 to the third power. 0.5 to the third power is 0.125 times 3 is 0.375. So rather than graphing these by hand, you might find it easier to type these into Desmos and get your graph. You can make a table in Desmos if you want to get a table, but the function is probably the easiest way to graph these. So we can type h of x if we want. That's what they say the function is equal to. 3 times 0.5 to the x power. So I can use this button to get to the x power. And there's my graph. You can see that it's decreasing over time, just like I showed. If we had put in the x and y values into our table, those should show up on our graph. But it wouldn't be enough just to have the table, because we want to see how those are connected as well. So the table part is optional, but you do have to have the function graphed. And if you did both, you'll see that all those points will line up on there. And then we'll take a screenshot of this. So I'm going to use the snip and sketch that Microsoft Word has in there. I'm just just trying to get that to be... Sorry, I messed it up. There we go. And we need our Desmos back. I was trying to get a copy of that, so here we go. We've got our functions that we graphed. We got the bit of the table that we started. And I'm going to copy that, and I'm going to paste it into my Word document. Make sure it's nice and big so I can see it. I can read your function, I can see your graph. And you'll do number 2 the same way as that. Alright, then there's a couple more questions here. And then we're going to talk about word problems that have to do with exponential decay. So exponential decay, as a word problem, we're going to use 1 minus r. So we're not going to use the plus, we're going to use the 1 minus r. And there's an example here of a motor scooter purchased for $1,000 depreciates at a rate of 0.15. Now they'll give it to you as a percent, but you have to change that to a decimal. So we're going to use 1 minus r because this is a decay problem, so that would be 1 minus 0.15 is the same as 0.85. And then you can graph that, like I did right here. And then to find when it's worth $100 or less, you can type into your graph y equals 100, or f of x equals 100, and you can see where the two intercept, the two functions intercept, and then that is your answer to this problem. It happens at about 14 years in this example. And then here's another example that's been done, so you can look back at here to see how this exponential decay problem works. And that example problem is very similar to number 7 on your worksheet. So we're going to look at number 8. Number 8 says a certain car depreciates about 15% each year. John buys a car valued at $20,000. When will his car be worth $10,000? So the initial value is $20,000. The interest rate is 15%, but as a decimal, that's 0.15. So r minus 0.1. So we have to do, that's supposed to be 1 minus r, sorry. 1 minus r is equal to 1 minus 0.15, which is 0.85. Or 0.85 if you prefer. Now we're ready to write our equation. So our equation is that f of x, that's just the function, you could write y equals if you prefer, is equal to the original value, 20,000, times 1 minus r, which is 0.85, to the x, so let me go back to the home, to the x for the variable, x power. And this is what we'll put over here. So I don't want these ones anymore. So to graph this, I'm going to have to change the scale, but I'm ready to put in my equation now. 20,000, don't use a comma in the 20,000, 0.85, you can put 0.85 if you prefer, and then to the x power. Now I don't see my graph because I didn't change my scale yet. I need to go at least, my y value has to go at least to 20,000, because that's my starting value. So now I can see where it starts. It starts at 20,000, and I want to know when's it equal to 10,000. So you can find that by looking at your graph and saying, well, it's about right here. Or you can graph another line, a horizontal line, where it's y equals, or f of x equals 10,000. And then you can find the absolute intersection between those two, and it looks like this will take about 4.26, exactly 4.265 years. Not years. So not that long before your car is worth half of its value. And then we need to attach our graph. You only have to attach one graph. You don't have to do one before you did this and then one after you did this. So you can do a link, or you can do a screenshot. The link button is right here. And then I just copy this, and then I can paste it right here. And then hit the spacebar once so it becomes an active link. And that's how you do that problem. There's another one. Oh, and then the rest of the problems you only have to pick 2 of. So there's 3 problems here, but you only need to do 2 of them. So for Each one you're going to write the equation and then answer these questions. So these problems have 2 questions each to answer. Let's look at number 9 is good. The cost of a new ATV, all-terrain vehicle, is $7,200. It depreciates at 18% per year. So let's write the equation before we answer these questions. So f of x, our function, is going to equal to our original value times 1 minus r. Well, r is 18%. As a decimal, that's 0.18. And then we have to take that to the x power. So 1 minus 0.18. Or you can use the 0.18 in the function in decimals, that will work too, is 0.82. So I'll just write it again, 0.82 to the x power. All right, now we're ready to, let's graph it first before we analyze this. We could change this to 7,200. And change this to 0.82, and that's our graph right here. I don't have to change the scale because it was pretty much set to work from the last one. All right, let's see the questions. How many years will it take for the ATV to be worth $5,000? 5,000 is right here. It looks like at about somewhere in here, 1 point something years, not very long. Or you can get an exact answer by 5,000. So after 1.837 years. So you would type that here. I'll let you do that. And then find the value of the ATV when it's 10 years old. So that's right here. This is the time on the bottom, the x-axis, the horizontal axis. So 10 years is about here. But we can also actually type in the actual x equals 10 and let decimals find the exact answer for us, and that is where those 2 lines intersect, so it's worth $989.63 after 10 years. So that's how you would answer that one. So start with the equation, and then use the graph to help you answer the other questions. If you have any further questions, let me know. Thank you.